Thank you, Nicole. I'm Alexa. I worked with Miistakis over the summer and it turned into an independent project I've been working on this fall semester, looking at the Salamander tunnels in Waterton Lakes National Park. So today I'm just going to share my findings and a little bit of the biodiversity that we found in the tunnels. So to start off, I'll go over a bit of background about the project. I'll go into my methods. I'll talk about my analysis, and then I'll just give a few recommendations at the end of things that I have learned over the time working on this project. So to start off, the very origins of this project start at the long-toed salamander population in Waterton Lakes National Park. These guys are found in a few pockets around Alberta, one of them being in Waterton. And so a bit of history about this population in Waterton. We'll talk about their migration, the population disruption, and then the installment of these tunnels. So to start off, as we all know, salamanders are amphibians, so they spend part of their time on terrestrial environments and then the other part of their time in aquatic environments. So our population in Waterton, they overwinter in terrestrial environments, and this has been found to be on the west side of the highway in this terrestrial area over here, and then they make their migration in fall as well as in spring back and forth to Lynette Lake, which is where breeding happens. Lynette Lake is a perfect spot for this because there's no native fish in the lake, so there is no issues with competition or the larvae being eaten. And so as you see, to get back and forth, they have to cross this highway. And this is where some issues come in. So in 1991, they did construction on this highway. They tried putting sidewalks up. And while constructing the sidewalks, the curbs of the sidewalks actually inhibited the salamanders being able to cross. And that's when this population was first discovered in Waterton. So heaps of salamanders were being found alongside the road that could not cross over. So in the early 1990s, studies started to happen on this population and characterize it, as we weren't aware of it yet. And between 1994 to 2009, there was a 65% decrease in the population, mostly attributed to road mortality. So it's being an increased issue before they characterized the 65% in 2009. They installed 4 tunnels under the highway running west to east in 2008. So part of this project has had some previous work completed before I came on. So 2 camera traps were installed and they were put in tunnels 3 and 4. These were active from July 9th to October 2nd. And so out of just species images, there was a total of 11,000 different images, about over 4,000 of those being actual species images. And as you can see, we got a lot of cool things, but we got no salamanders in our population. So we got garter snake, clumping ground squirrels, and deer mouse as most notable, as well as we got some boreal toads in this population, but no salamanders over this season. So I'm going to talk a little bit in depth about the actual cameras. So at the top, we have a regular motion sensing camera. As anyone who's worked with camera traps knows that these use thermal heat to detect motion, which is really great for mammals, but when looking at reptiles and amphibians, because they are ectotherms, they do not regulate their own body temperature. They often have a lower body temperature because they use the outside environment to regulate that. So with lower body temperature comes lower detectability. So to bypass this, we use what's called a HALT, stands for Hobbs Active Light Trigger. And about a centimeter above the bottom is a little light beam that runs end to end. And when this light beam is disrupted, anything comes across it, it will trigger the camera to take a photo as well. So we have higher detectability with reptiles and amphibians, but this also means anytime anything goes on top of this HALT, it also will trigger photos. So for my work, I created camera traps, 2 of them. We put those in tunnels 1 and 2 at the end of April. We also replaced the battery and SD cards in tunnels 3 and 4 where the camera traps in the previous year were. And this is just a map to give some context to the camera traps. So in tunnel 1 and 4, they're on the east side backing onto Lynette Lake. And in tunnels 2 and 3, they're on the west side backing onto that terrestrial environment. The tunnels do slope down a little bit from west to east. So tunnel 1 and 4 on a bit of a slope where gravel may get pushed on top of it. And this does become a problem later on. So when looking at total images captured, we got a lot. You can look in 2025, we had 4,000 Columbian ground squirrel images. Does not mean we had 4,000 Columbian ground squirrels moving. That's just the pure amount of images. So it works out to a little over 13,000 species images within the 2 years and over 100,000 images that had to be processed. So our most notable ones, again, were Columbian ground squirrel, deer mouse, and the wandering garter snake. And so we also got long-toed salamanders in 2025, which was super exciting to see. We had 105 images total. So to create these from images to actual events, I had to use the time of when the images were taken to create species events. Because of this, we had a malfunction with the cameras for a small period of time where the images, the date was not recording properly and neither was the time. So all those images had to be removed for this analysis because we could not characterize species events as there was no accurate time. But removing that, these are all the species events characterized. So we've gone from seeing 4,000 images of Columbian ground squirrels in 1 year to having 291 events. So those numbers go down quite a bit. And again, our deer mouse are the highest observation, following our garter snakes and our Columbian ground squirrels. So when we look at usage between tunnels, I'm going to talk about the 3 most prominent species, just to give some context. So when we look at this image, our 3 most common species were the deer mouse, the ground squirrel, and the snake. So if we're assuming that they use all 4 tunnels equally, we just see equal amounts per tunnel. And that would mean that we are expected to see 231 deer mice crossing the 2025 season. However, that was not the case, with our highest number being in tunnel 3 at 318 and our lowest number being in tunnel 4 at 156. Similarly, with the Columbian ground squirrel, we should see about 73 events in 2025. Those numbers varied quite a bit, with having 275 of those events in tunnel 3 and only 1 event in tunnel 1. And again, our garter snakes, we should have seen about 30 snakes crossing in 2025. Again, very, very different numbers, 72 in tunnel 3 and 1 crossing in tunnel 4. So why do these numbers vary so much? That goes down to our camera effort. So I have our 2024 season, our cameras were not active over the winter, and then we have our 2025 season again. The cameras that are in green are on the east side, and cameras that are in purple are on the west side. So the east side cameras were on a bit of a slope. So anytime water came through, a lot of gravel got pushed up onto the hulls and caused them to essentially auto trigger, sometimes until the cameras died. So that camera effort was a lot lower due to those malfunctions. So our west side cameras worked pretty well, while our east side cameras did not. And to account for this, we had to subsample the total working days based on the lowest amount per camera. In tunnel 1, that camera had the most malfunctions. We only got 22 working days. So for analysis, that camera was actually removed just because the number was too low. So our analysis includes tunnels 4, 3, and 2. Again, all subsampled to account for evenness of working days. So by removing the tunnel 1 data, we lost a couple observations because it was the least effective camera. We didn't lose too many. So for amphibians and reptiles, we lost 7 boreal toads, and we lost 17 observations of water and garter snakes, and all the observations summed to 306. So looking at biodiversity, this is the Simpson Diversity Index. The closer the numbers to 1, the greater the biodiversity is. So we can see here our biodiversity is the highest in tunnel 3 and the lowest in tunnel 4. So when we look at our species per tunnel, this is our 2024 year, we can see that not only do we have a longer list of species in the tunnel 3 camera, we also just have higher amounts. Whereas in tunnel 4, we had less species and often lower amounts. But the same trend can be seen in the 2025 season. Tunnel 3 had the most species with the highest amounts. And then we go to tunnel 2, ending in tunnel 4. So reasons why tunnel 3 might be the one that's most diverse or used come to, first is the tunnel appeal. So different entrances can actually impact if a species is likely to use the tunnel. And that could also, well, all the tunnels are built the same shape, just the environment around the tunnel can impact that, as well as the precipitation. We had lots of amphibians in tunnel 3, and it is theorized that this tunnel has the highest precipitation just based on where it is compared to the other tunnels. So that would make it more likely to be used by amphibians. The camera direction also would impact this. Again, our camera was on the west side, and the west side was more easily accessible than the east side most time due to gravel or water filling the tunnels. And another thing would be predator-prey relationships. We saw a lot of species interactions that were really close in timing. Some of them are known predator-prey relationships. So those could impact what species is using what tunnels and which species may be following behind. So now to talk about biodiversity metrics, we're going to talk about evenness, richness, the Shannon index, and then the Simpson index. So for evenness, it's just going to tell us the balance between each tunnel. So here we can see that in tunnel 3, again, we have the most species, but tunnel 2 and 4, we see a similar balance of species. Looking at richness, we're looking at the abundance of species. We have the most species seen in tunnel 3 at 19, and then we have 12 different species seen in tunnel 2 and tunnel 4. Looking at the Shannon index, this is going to account for our diversity, but the Shannon index also allows us to account for those rare viewings, which we had quite a few of, species that were seen a couple times. Similar, tunnel 3 is going to be our most diverse, with tunnel 4 being the least. And our Simpson index allows us to test for biodiversity looking at dominance. Again, there were no species that were overly dominant. Everything was pretty even. So we see pretty consistent results between all 4 tunnels when looking at these biodiversity metrics, with the big takeaway being that tunnel 3 is the most diverse and the most used. So recommendations I have just from working on the project. When possible, I think having camera traps at both ends of the tunnels would be really helpful. It would help us monitor passage through the tunnels better. And there are also a few instances where one species would enter the tunnel, and between a minute to 2 minutes later, the species would exit the same species would exit the tunnel. And when we can't confirm it's the same individual, it often would be just given the distance some of these smaller species can travel. So seeing what makes a successful passage through the entire tunnel would be helpful to characterize what's using the tunnels, whereas what's just entering and leaving the tunnels. It also would help improve the camera effort per tunnel, because our east side, while the data is valuable, it can tend to be a little bit problematic just given that slope and the gravel in the tunnel. So by having traps on both sides, we just get better camera effort. Even if one side's malfunctioning, the other side likely wouldn't be. Another thing is frequent site checks. This is hard because it is a remote project. It is 3 hours away, but replacing the batteries more frequently, I think, would be a good idea. Something that I did not account for on my time working is that we would get more usage in the summer months as opposed to the spring months. So when I checked on it between April and June, most batteries were over halfway full, so they were not replaced. And then those batteries died mid-July just because there was more usage and the cameras being triggered more. So that would help, as well. Just being there more often can troubleshoot any issues. So we had SD cards not working, just camera malfunctions, things getting on top of the halt or the halt's moving. So the more often we're there to check on it, the faster we can troubleshoot any of these issues we've seen. As always, I'd like to give a big thank you to the Alberta Reptile and Amphibian Society, as well as TD Friends of the Environment Foundation for being the funders of this project. I'd also like to acknowledge the Miistakis Institute, as well as Waterton Lakes National Park. And I'd also like to give credit to Dr. Sarah Smith for helping me with this project as my supervisor, as well as a lot of the coding, and Dr. Dorothy Hill for helping with species identification. I can now open the floor to any questions.